Um, okay, so yeah, welcome back everyone. I noticed that we're smaller in number today, so we're quite interactive or a bit more relaxed than yesterday. Feel free to ask lots of questions. So we'll begin with just a quick presentation on what CNNs are. It's similar to yesterday's morning session where we give you a bit of the theory, and then we have a notebook that accompanies these lectures, this lecture. We probably won't have time to go through it all today. To be honest, most of it is quite similar to yesterday. The first 3 or 4 exercises require a bit of discussion, but after that, you can attack it yourself. You can have a go at it yourself. So I'll also go through a bit about some of the things that we could do to improve the performance of yesterday's network. But I'll begin with Isaac, so go ahead.
Yeah, so we're going to have a quick overview of CNNs and how they work. So CNNs or convolutional neural networks are different to the 3 fully connected neural networks that we looked at yesterday. And these networks, they really excel at things like image classification and working over image data. And you can kind of think about it in this way, because when you have fully connected neural networks, you have a bunch of input data, and then you pass that data and propagate it through the network. So you can imagine yesterday we looked at the Penguin class, and we had a few features that we were using to train the model, and for each feature that you would multiply it by a matrix. So you can imagine if you had an image, just a 10 by 10 image, then you would have 100 features. And then if you had like a 1,000 by 1,000 image, then you would have 1,000,000 features that a fully connected neural network would learn. So a CNN overcomes this problem by using something called convolutions. And essentially, convolutions are done on the image data, and then this allows the network to not depend on the input size. So regardless of the input size, you can have roughly the same amount of parameters. And we'll look at why this is so. So a few features of convolutional neural networks is that the convolutional layers are translationally invariant. So that means if you're trying to find a dog in a picture, it doesn't matter where the dog is in the picture. So you can translate the dog in the XY plane of the picture, and then a convolutional neural network will be able to still recognize it. And it's important to note that CNNs are not rotationally invariant. So you can imagine having a picture of a dog and then rotating it 90 degrees. And then if the neural network hasn't seen that before, then it wouldn't be able to recognize that as an image of a dog. So we can address this by using something called data augmentation. So that's essentially making a copy of the image and then rotating it 90 degrees or any amount of degrees. And then thereby you're generating more training data of the dog or image in different rotations so that the neural network can see it and learn from it. So you can look at roughly what convolution is. So convolution is like having an input and you have like a kernel. So this would be a 1D input, and then this would be a kernel of size 3. And then essentially what convolution is doing is it's taking the input, and then this kernel will be a set of initial randomized numbers. And essentially you're you're multiplying the input by the kernel value in all of these three places. And then you add them all up, and then you get the first output in the output vector. And then you keep on sliding along, and then you get the second, third, all the way to n. And then for here, for a multi-channel output, you would have the input and then an example kernel, and then you apply the same logic over here. So instead of just multiplying over a single channel, you would multiply over all of these 9 values over here, and then you'll get a single value in the output. So multiplying this input channel by this kernel will give you an output vector just like this, and then multiplying it by 4 different kernels will give you this stack of outputs. And for 2D kernels, for 2D convolutions, you're applying a similar principle. So you multiply, you have the kernel and the 2D data, and then you're multiplying each of these points, and then you'd get a single point over here. So I have a animation of what's happening. So essentially you have 5 by 5 inputs, and then you have a 3 by 3 weight. And then essentially this input over here, this kernel will be multiplied by this 3 by 3 grid in the input, and then it'll give you this first output over here. Yeah.
And these weights are then learned during the training process.
Yeah. So these are learnable weights. So since they're learnable weights, you also need to apply nonlinear activations to them in order for it to learn. And if we have an overview of a typical CNN, you would have your input, you apply some convolutions, and these convolutions learn some features. So
You have to click on mine.
So you can think of convolutions like learning some features. So you have some learnable weights, and then once it goes over a feature that's been trained for, then it will output a value in the correct place. This is an overly simplified view. Normally it's learning lines and not a big feature like a life. And then once you've learned all these features, you can just flatten all the features and then pass it to a fully connected neural network. And then this fully connected neural network will basically learn how to combine the features. We'll learn how to combine the features, and then it can output the correct class. So important thing to note is that if you have images, of different sizes, this adaptive average called 2D will essentially take all the inputs of different sizes and then output image-like data on a single size. And this is how you're able to ensure that when you have different sizes passed through the networks, the parameters don't scale.
So is that 1 by 1?
Sorry, one by
So what do you get? What's the output size of the adaptive?
that could all
Is that
be,
anything you want it to be, or is it a single? Is it a scalar?
it would be a 2D image, and then you'll need to flatten it
Okay.
and then pass it to the fully connected neural network.
So does it map it from a general 2D image to like a fixed size?
Yeah. So with this look at the documentation. So here it shows it quite well. So you would say you want a output of 5 by 7. So you could take a 10 by 10 or 15 by 15, and it'll just output a 5 by 7. And then in this way, it's able to keep the number of parameters in the fully connected neural network the same size, no matter what input size you have.
So does that mean I do not need to input pictures of the same size?
Yes, you can have different sizes if you're using the adaptive layer. If you use a different, just a normal full 2D layer, then you'll need to have the same size. It doesn't have-
Whether that works well is another question. I would
Okay.
say that you should try as best you can to keep your inputs all at the same resolution.
Mhm.
We, in our examples in climate, we tend to train different models on different resolution data sets. Yeah, just something to bear in mind that what works for one problem might not necessarily work for another.
Yeah,
Mhm.
So in that example, sorry, I asked questions. In that example of on the slide, are you basically using the adaptive pooling to go down to a one by just a fixed, just a one-dimensional?
you can,
Back to the slide. Yeah, so that is that demonstration just going from like 2D data to a single.
yes, you can also,
Yeah.
you can also just pass in a number and it will give you a vector instead. So it's can go from like a 5 by 5 to a vector.
So that's giving you basically putting it in a format where you can use a linear classifier.
Yeah,
Another question, just to make sure I understood correctly, and the convolution, I mean, it is downsizing in some way, but it's making sure that the part that I'm interested in the picture is kept, right?
yes,
Okay.
And it doesn't have to downsize either. So in that example that Isaac showed, it does downsize because the kernel, it meets the edge of the image.
Yeah,
You can add padding to the image. That could be random noise.
yeah,
It could be constant extrapolation. You can essentially keep the learned feature map or the resulting feature map the same resolution as your input. It doesn't have to downsize.
so you
Pooling is what's used to downsize, and that's something that we're going to discuss a bit later.
yeah.
yeah, so you can add padding if you want to keep it the same size. So that pads the number and you get the same, if you get a 5 by 5 input, then you get a 5 by 5 output. So there's different things that you can, and you can play around with this later to understand it better.
Thanks. Morning.
Yeah, I think that's not.
Okay, what I'm going to do, even though we don't have much time, is just go through a bit of the exercise from yesterday first. So what am I doing? So the point at which we left yesterday, the network was performing quite poorly. Did anyone? I've spoken to a few of you, but has anyone else managed to improve that since yesterday? Or okay, well, I had a go and it took me a bit longer than I was expecting to improve things. So don't worry about doing all this now, but you can refer to the solutions and see how it's done there. But in summary, you have to apply. We don't normalize the data ahead of time, so we don't subtract the mean and realize our standard deviation. This can be done in a number of ways, but for the demonstration, we've had to use different neural network layers. We apply this batch norm layer here. And we apply this repeatedly throughout the network.
What does it do?
It normalizes the data in between twice suppressing mean and standard deviation.
Okay.
The input data, and it also is running means or statistics from the data. So it normalizes on a batch basis and also computes running. Yeah, so the first layer will normalize all of the input features.
Okay.
The second one, the output of the linear layer will produce another set of sort of learned features.
Mhm.
And well, no, not learned features, but the features that are learned are applied to the to the inputs there. And that will then be normalized by some mean and deviation as well. So it just keeps the values in some kind of easier to use in an easier to use range, so they don't blow up.
And we don't care about that after the last linear.
No, because at the last linear, basically we can feed that raw log its value into a loss function, which applies softmax. So yeah, the key thing is that it also computes these running means and standard deviations, the statistics on your data set. So when I was talking yesterday, I mentioned that during training, we have these two modes. Is the model.train and the model.eval. When we run in evaluation mode, we utilize these learned statistics, these running metrics, these running statistics that are decreased. We don't want to, when we run validation, we don't want to compute the mean and the standard deviation on a batch level. We want to use the mean and the standard deviation on the training data. Okay, so in terms of implementation, it's a case of adding these layers. And we also need to apply this drop last equals true to the train loader. So batch num does not work when the batch size is equal to 1. This is only 1, is it? So it will throw an error. So you need to, if there's one example left over when you iterate, which I believe is the case here, though I haven't shown it, but there is a case here, it will fail. So you can have a go at that yourself.
I'll just try it for.
Does that always drop the last one, even if they were all the same size? If you say drop last equals true, does it get rid of it?
That's a good question. I don't know.
I'm not sure, but I would assume that will drop it if the last batch is but if it doesn't equally divide, then it drops it.
Makes sense.
Sorry, I wasn't just half as why is it so important we got the last one?
Because if the last batch size has size 1 instead of here we have 16. So if the total data set isn't a multiple of 16, we get a remainder of 1, 2, 3, 4, 5. If it is 1, that will lead to an error.
Why?
Because the batch norm there cannot compute batch level statistics on the batch of size equals 1.
You'd be doing like the mean of one value will be itself, so we would just get 0.
You can try this out. I think in this particular case it just leaves you an error. So
Yeah, it did.
Okay.
That was the problem I had.
and then finally I increased the number of features. I think I only presented to you two, only showed utilizing 2 features. I think I just decreased this to 4 or 5. No, I should have added another one, but 4 does the job.
This one with 2 already has pretty good
Is it?
confusion metrics.
Okay. That might be the case. Yeah, that looks well. Okay, so that's probably not needed. So 2 features is enough to discriminate between the separate classes reasonably well. So this is quite a trivial problem to solve. So let's move on. Are we happy to move on to the end list notebook? Is that okay? Okay, so we're going to be working on this MS data set, which I'm sure many of you have already heard about. It's one of the simplest vision data sets that you can use. That's not to say it's completely useless. It's often useful to use to make use of these data sets to just benchmark your model. So if you've got a very complicated model, you're not sure if it's working, then you can always refer to these simpler data sets just to test that the whole pipeline works. So I think they still have value. They've kind of been superseded now by other variants of vision data sets like ImageNet. What else? Fashion MNIST. So MNIST is seen somewhat as a trivial problem to solve. And now it's quite simple by modern day standards. So today we're just going to train a very simple convolutional neural network to try to classify images of handwritten digits from 0 to 9 into simple classes. This data set has 60,000 images in total, training data, and 10,000 test images. There's a really good question I think you asked yesterday that normally you'd use train, validation, and a test split. In this case, we already have the test split ready for us. We actually even use that as validation. So, but if you want to have a separate test, train, and val, you'd have to split the training data into a separate data set. And that's just we're not going to do that today, but we'll use the test as a validation as well.
I have a question about data set size, because the one we used earlier, the penguins, are just about 600 or something, and this is now 16,000. What is like good number? Like when would you say, oh, this is too small to do like reasonable training on it?
So there are probably lots of rules of thumb, and I apologize for being quite hand-wavy when I explain this, but you probably heard that neural networks are called universal function approximators. So in theory, given enough data, you could approximate any function to sort of map your inputs to your outputs. For the MNIST example, I apologize if you've all heard this before, but it's quite a complicated mapping to make. The data set is very high dimensional. So 28 by 28 is each image. So the harder the mapping between your inputs and the outputs, the more data you tend to need. That's kind of a very hand-wavy explanation of how these things work. So of course, there are architectural choices that you can make to like convolutional layers, which without these, if you do like a 28 by 28, that will be your sort of first input to your neural network. That's incredibly difficult. It's not helping you in any way to map from your inputs to your outputs.
So the more complex, the more better, basically. Okay.
That would be a faster way of saying what I just said. Okay, so let's just begin by consciously half an hour left of this session. This always goes slower than you expect. So the first cells we've done all for you. You just download data. You can set down from true to false if you really want to. This will just see if it's already cached. If you haven't got it, we'll download it. I think I already have it, so it hasn't told me that it's. Okay, so I've got 60,000 images. I thought it was 70,000. Interesting. Yeah, but I downloaded the whole data set. Okay, well, it's apparently 60,000 data points, not 70,000. So what we can do is, before we get onto transforms, which we talked about yesterday, is we can just print this data. So I always forget how to do matplotlib stuff. Don't worry too much about this stuff. But I always forget the syntax of this. So wrong.
It was the plots, do you know how to?
Oh, yeah, I do, thank you. It's, and then for index. Targets. Sid. Don't copy my, I do make errors, so. Oh, actually, I was in axis here. So axis is basically axes is like a NumPy array of data. So I need to do axis dot axes dot flatten, which flattens the array. Then when is that fine? Okay. So that took me a long time to do, but essentially I'm just putting the first 5 images of the data set. Do you know how to get the title set titles it? Yes. Oops. Okay, so we now have our targets attached to our image data. So you can see it's 28 by 28 with a label 5, 0, 4, 1, and 9. So the next step is to, because Isaac said that the data is CNNs are translationally invariant, but they're not rotationally invariant. So we need to apply some transforms to augment our data so that if we observe a 1 or 2 that's slightly off axis in the wild, we can be assured that our model can detect it or predict that the 2 is the 2. If you think of just training a classifier or filter to detect, say, edges, so vertical edges, that will do a really good job of detecting a 1. But if we slide the 1 just to like a 45-degree angle, it's going to do a less good job. So this is pretty much quite similar to yesterday. We have basically the MNIST data set has already done a lot of the work for us. You can just get this from this import, which we did here. So like we had defined our own data sets yesterday, you can actually just import data sets from Torch Visual data sets, or load data sets that you can download. So the first thing to do, I'm trying to remember what the process is here. So as before, we have a train set, which is specifically has training transforms applied and a validation data set with image transforms as well, with training set to false. So this calls a function defined here. If training is set to true, we do some specific augmentations to the training data set. Is that all kind of clear?
Yeah,
So
does it just append some other training data, or does it change the picture that we are having? I don't think. And just then continuously, like, do I keep my original here and just add some more transform ones?
yes.
Okay.
So we don't. So one way of doing it, like Isaac said, is to create offline, you create loads of different augmentations of your data set.
Yeah.
Here, we're not going to do that. We're just going to apply different random transformations on the fly when the training process. There might be performance reasons for doing what Isaac said. Would you agree? Like if you want to avoid doing transformations?
Yeah, I guess
ahead of time?
you'll only do it once, but you'll have, use extra spaces, all that.
Yeah, I mean, in theory, with the transformations that you're given with PyTorch, you have an infinite availability of different things you can apply at training time. So I would argue, if you're not constrained by performance, why would you do it ahead of time? Right, so the other kind of subtle point about this is that we're using a list of callable functions. This was presented in the optional exercise, I think the task 4C or something yesterday, where you have a list of callable functions like tensor or lambdas here, and you use this torch vision.compose. Where is that set? Torch vision compose on the transform, and that basically daisy chains all of the transformations together. A question might be, why do we apply transformations at all? Well, why don't we apply transformations to the validation data set here? Really what we want the validation set to be is a completely consistent evaluation, a completely consistent way to evaluate our model. There are also a few things that you might be interested in about. So what is this lambda doing? So we're going to be using a model called, what is it? MobileNet. We're not going to define our own model in this neighborhood. And this relies on the inputs being RGB. So, and that's why we have a 3 here. So we basically copy the data set. Well, we forecast the data into the RGB channels.
Okay.
I think that's everything. We're missing something.
What? I don't know, maybe it's a stupid question, but the target transform, are we still going to define them?
Yes, we are. Yeah, there's also something here which might be a bit weird. We've been muting the data set, so we have the channel dimension last, and the height and the width first and second. Now, I believe, and I'm not sure if this is accurate, but PyTorch expects when you run 2 tensor on your data set, it converts it into channels times height times width. The default format in that matplotlib expects is height times width times channels. And the reason why it puts channels first is that PyTorch is optimized for running on GPUs. Having channel dimension first enables you to utilize your threading and your blocks in a GPU more effectively. Just the memory layout is more optimized for GPU. So the memory is all contiguous the data is all contiguous in memory. So you're not hopping around all the time, and it doesn't incur additional latency. You make use of maximum bandwidth from the GPU. So these are just some things to kind of, if you're concerned about why tensors are in a completely different format, that's kind of the Hamilton justification for that.
Okay.
So we're going to apply some transformations. So we've already kind of mentioned one, and that is random rotation. What you can do actually, it may be just a few minutes, just have a look at I feel like I'm talking a lot, so is just look at the things very good. Yeah, have a look at the torch transforms. I think we just go to this link here, torch transforms, and in fact I think it talks a bit about what I just mentioned here, channels height times width. You could do anything, there's loads of stuff to choose from, and actually that would be quite a fun task. If we don't have time today, just play with transformations and augmentations with this, it's quite fun to do. So yeah, just have a look at the documentation, pick out anything that might be of interest to you, and we can talk about how to implement it. I can show you how to do one of those, random rotation. That's one that we could do. I should say, I think the torch tensor transformation also does something a bit more than I said. I think it normalizes the data between 0 and 1 as well. You know, we can have a look at that. So at the moment we have pixel values between 0 and 2.5. Yeah. It is. Remember some. Has anyone tried anything else or heard of anything else? If there's these you do random plots, you can get sub plots to move the way around. But maybe if you just want to print them out and have a look, actually we would have done spoiled. Let's see, I think it's okay. Data version. Isn't weird.
Sorry, trace. That's super, super.
Sorry about this. It's just the index, well, it will be because we're using enumerate, and then the axes.
Print it and don't make it.
I mean here,
Looking for the initial target or training. You do the train set.
maybe I set the target transform correctly or something. Is that correct? Right. This neutral as well. Change. It's an error there, so I think it's something to do with the transformer, fine. Yeah, this is only plotting, it's not that important, but it is frustrating that I can't show you the resulting transformations. That's right, I need to set a function. Finding transform. I think it's just tensor, and that's why. There's two tensors in image-based transformation.
Yeah.
That's what I'm doing. Yeah, that was going on until that was an issue, but So the solution is passing a function to it with a variable of your target index. Um, and then you should see some random rotations. Sorry, that took so long. Yeah, so it's just defining a function which takes your target index and passing that as passing that into your target transform random.
Was the issue that you were calling tensor the function calling rather than just passing?
Yeah, I think it was. Yeah, now you mention it. Yeah, I think this could be done a lot simpler with just that. Thank you.
Yeah, was only when I saw the solution that was like, oh,
Yeah, so you don't even have to define that function. Tensor should do it all for you. Yeah, that was a subtle error that I should have anticipated. Okay, so as we talked about, we don't have much time, but this is kind of, if you've got everything from yesterday in terms of training the neural network, there's not really much extra to do, and you can probably do it in your spare time. The only sort of thing is setting the device, which we'll try and get through by the end of the session, and creating the model. So we have a data set, took longer than it should have done. We need a model, we need an optimization routine, and we need a loss function. So we'll create the data set as yesterday. Data train loader, or train loader, sorry. Equals data loader. Batch size equals 64. Triple through. What else? There's a num workers parameter which is useful here. I'm going to set that to 4. Also the data set and data set. And then let's just do, shouldn't really copy and paste code, but the interest of time, let's just do that. Triple is set to false by default, but I've set it as that the clarity. So in image problem setting num workers is almost certainly required. It parallelizes the augmentation and transformation of your batch. It doesn't do it, it does it on a per batch level. So we don't parallelize batches independently, we just go through each batch and apply the transformation to it.
you mean each worker has one batch each, or?
I think all workers have a single batch.
Okay.
I think. So there's another optional thing you can do. If no one has a GPU on their laptop, you can always reduce the data set size, and I've added that just in case. Because if you follow through this notebook, what you'll find is that each epoch takes about 10 minutes to do. Well, at least it takes that amount of time on my laptop. So if you have a GPU, it will be a lot faster, but you'll also find that the transformations are done on the CPU. So it still takes quite a long time. I can't remember off the top of my head how long it takes, but when I was doing this last night, it was still taking a while on my GPU machine. I was trying to figure out how to pass these transformations onto the GPU and utilize the GPU for that, but I didn't get around to it. But maybe that's a task that you could try to solve yourselves. Okay, now we have our data loaders. I'm not going to do this now, but maybe if we have time, we have 6 minutes to do this. Okay. So we're going to use this mobile net model from Torch Vision. There are loads of models that you can extract from their website. We also initialize it with some pre-learned weights. We've chosen MobileNet because it's pretty lightweight and it's not going to burn or melt your machines. So as yesterday, just print out the model. It's not very informative looking at these descriptions, I don't think. I don't know if you can really get a lot out of that. There are lots of better, if you go to the paper, or lots of better visualizations of how these things are connected and how they're constructed. So don't rely on this as a learning tool. I don't think it's that useful. And you can see that this has been initialized with some parameters. So if we just do model dot parameters, yeah, I need to, it's a callable, so I need to put a list on it. So yeah, these are the learned parameters within that model. You don't have to change anything in this. It's just showing you what the model's all about. Okay, so if you look at the final layer of this model, you'll see that the number of output features are 1,000, and this isn't going to work for our task because we only have 10 classes. So this has been trained on a problem with 1,000 classes. We don't want that. We want 10 classes. So what we're going to do is just modify that final layer. It's as simple as that. Probably better if I didn't hard code it, but it's easier if you did that. And we can just verify that has changed. See that's changed to 10. It's not particularly very general code because these model.classify at the end, their names change regardless. These names change depending on the model. So what you can do and what we've linked in this repository is Jim's package called Torch tools, which provides a wrapper around loads of different convolutional models and ensures that you can index these things and modify the output layer to suit your problem. For a bit of added terminology, we're modifying the last layer. We're actually doing something which is quite a grandiose way, transfer learning. But really what we're doing is we're fine-tuning the model. We're training the model from end to end. We're not just training this last layer. You could just train the last layer and use the whole the initial encoding part of the model as like a feature engineering step, but we're not going to do that here. It'd be quite an interesting thing to play around with. But we're going to train the model from end to end, but using these initialized weights use the initialized pre-learned weights. You might ask, why do we use initialized weights for a problem which is completely different to what we're doing now? It turns out for many vision problems that if you train on a completely disparate data, you still learn quite salient features about salient vision features like edges. Edges is being one of them. Things like that.
Is it like starting from a base that is similar to your application?
Exactly. Yeah.
I guess all images can be built up with lines in different directions. So typically the earlier layers would have more general features, and the later layers will have more specific features to the data they train on. So typically you might say I want to keep the first layers which have more general features, and then they keep those constant, and then just train the later layers.
I think as I understand it, the first sort of layers that you learn in a CNN are quite easy to interpret, but the deeper and deeper you go, the more confusing they become, like how you can, and that's one of the problems with CNNs is that they're very difficult to actually interpret how they come to the decision that they come to. Because the learned representations are so abstract. There's a really good blog post here actually, which is I'm just going to plug Kolar's blog. He's a research scientist at Anthropic. He's got a really good post on just even visualizing the MNIST data set. So like yesterday, I applied UMAP to the Penguins data set. Have a play around with that. That's something that I haven't included in the notebook. It's kind of done it for you here, but it's quite interesting to see sort of how all of these fancy visualizations, how they work. And I think he applies various different dimensionality reduction algorithms as well. So yeah, did T-SNE just to show how it can be represented in 2D. And that kind of points to how simple the data set is really. Okay. So as before, we're going over time, sorry, but I'll just leave it after this. But we just need to create a loss. And then the Adam optimizer. Then it's a case of just following through a lot of what we did yesterday. But unfortunately, I don't have, because I just stashed all of my changes, I don't have that problem. Well, I actually have the solution sentence. Yeah, so it's just a case of defining these functions. And I think I made a mistake. So that's going to be model parameters. Yeah, so the only sort of thing to think about for training these things is that we need to define a device. So I am going to be running a CPU. This will catch GPUs if they're available, and the language of choice for NVIDIA GPUs is CUDA, but there are other languages as well that you might need to be aware of for other GPUs, but I don't have one of those, unfortunately. So yeah, I'm not going to implement these now because we're going over time, but it is just a case of taking what we did yesterday, iterating over the training loops, iterating over the training data and validation data. And the only thing you need to really think about is when you link variable data loader or batch targets in train loader. You need to move your data set to the device. So like here, you can move the model to the device if you're running on GPUs. It doesn't matter if you're running on CPUs, but if you are running on GPUs, you need to do this. And that's essentially it. Sorry that I can't go through everything. Or you can have a break. Are there any questions? Sorry that we couldn't finish the notebook.
And the work solutions.
Yeah, all the work solutions are there, so, yeah, have a go at it yourself first. It should be pretty much exactly the same as yesterday. So if you got as far as training the penguins data set, you're good to go.